Okay, question one, find the following terms. Strong acid, it's important we use that particular arrow. Those completely ionize. Strong base, we need that arrow. Those completely dissociate. Weak acids, we need our double arrow. And weak bases, we need our double arrow as well. And both are partial ionization. So we've got complete over here and partial for these two. So let's get right to it. So we're just going to look at kind of the keywords. I'm going to underline them. Write a complete, that tells me I'm using this arrow. Dissociation, bases dissociate. So I know this is a base and I'm using the Arrhenius method. So I'm not involving water. So we're just simply writing KOH with your aqueous. And we're breaking it up into the two ions, which are K and OH. It's aqueous over here. It's still aqueous on this side. Again, forgive me for these awful aqueuses. They are hard to make. And then our charges. Potassium's +1 on the periodic table. Hydroxide's -1. Next one, complete. We need this arrow. Ionization tells me it's an acid. And Bronsted-Lowry means I need to involve water here. So I'm going to write H2O in the liquid state. And then I'll write our acid, which is some weird one here, HFSO3, aqueous. Add those together. So this should be a similar question from what we did the other day. We know acids ionize. We know they give up hydrogens. So we're going to move one hydrogen from this compound. So we're going to be left with FSO3. And H2O is now H3O, not a surprise since it's ionizing. We know that's always +1. That one ergo has to be -1 and include your aqueuses. And we could write out the pairs in this situation, but we're not going to for this question because it didn't say to. Number 4, partial. That means double arrow. Dissociate means base, so I'm thinking OH here. And Bronsted-Lowry means I'm using water, so I better write H2O, liquid. There's our base, NaH3CO3, aqueous. There we go. Now it's a base. We know we need to make OH if it's a base. The only way we're going to make OH is to take our water molecule here and take off a hydrogen. Right? So we leave that, or we remove that hydrogen, we're left with OH minus. That means our hydrogen's moving over to this compound. There's probably a couple of ways you could write it. I'm going to write it as NaH2, CO3. And if it's gained a hydrogen, that means it's now +1. Both things in the aqueous state. Again, you could do your pairs, but I'm not going to do it for this question because it didn't say to. Number 5. Partial means double arrow. Ionization means I'm moving some hydrogens. Now this one's the Arrhenius method, so no water involved. So we're just going to take HSO3, that's aqueous. There are 2 hydrogens. We've been used to moving one. It does say here to move all hydrogens. So how many hydrogens are there? Well, there are 2 of them. They are plus. And what are we left with? SO3 -2, no pairs to do anything with. 6, dissociation, strong base. Oh, I'm using that arrow. Arrhenius method, no water. This should just be a simple one here. So NaOH, aqueous. Let's break it up into the 2 ions, which are Na plus and OH minus. Everything's in the aqueous state, as you can clearly tell by me writing aqueous. Good, next one, partial, double arrow. Dissociation, NH3, Bronsted-Lowry, so I need water here. Liquid, NH3. You've probably seen this one in the past, but it's a good one to review. Now we know it's dissociation. It's making a base. We know we need to make the OH minus molecule here. And how do we do that? Well, the only way we can do it is to take a hydrogen from water and move it over to NH3, which makes it NH4 +1. And again, you could do your pairs, but we're not going to do it in this particular question. Number 8, ionization. Strong acid, HCl, arrhenius. So it's strong. We'll use that arrow. HCl. Aqueous. No water involved because it's arrhenius. So H plus and Cl minus. Those are the charges from the periodic table. They also happen. Well, that's their charges. That one's done. All right, so this question's asking us for ionization equation for the weak acid H3O plus using Bronsted-Lowry, so we're going to need water. But then it goes on to say we're only going to transfer a single hydrogen. There are 3 hydrogens in this particular acid. It means it's going to take me 3 steps to do this. So let's do that. Let's do our 3 steps. So first thing, we'll start with H3PO4. And we're going to combine that with water because it's the Bronsted-Lowry method. And it said it's a weak acid, so we'll use double arrow. So first step should be no issues, I would hope. We're going to take a hydrogen from our acid and move it over to the water. So we're left with H2PO4, that's -1, aqueous. And we're also making hydronium that is +1. Now, what I'm going to do is I'm going to take this thing and rewrite it here. H2PO4 -1, and I'm just going to kind of repeat. So I'm sort of pretending that this is what I'm starting with now. So we'll add that to another water, put our double arrow in, and this is still acting as the acid. So we're going to take a hydrogen and move it over to here. So now we used to have 2 hydrogens. Now we're down to 1 hydrogen. We had a charge of -1. We lost a positive. Now we're at -2. And once again, we're making H3O hydronium. To finish this off, this thing still has a hydrogen here, so I'm going to rewrite it. HPO4 -2 plus H2O, double arrow. I know I missed a few aqueuses there, please forgive me. And what we'll do is we'll take this final hydrogen here and transfer it over to water. So now we're left with PO4. It was -2. Now it's gone down to -3. And we've removed all our hydrogens. Now it's probably smart at this point to kind of make this into sort of a math equation, if you will, cancel a few things out because we've got some things that are similar because we did some rewriting. So this compound was on the right side of the arrow and it also appeared on the left side of the arrow. They're gone. This was on the right side of an arrow. This was on the left side of the arrow. They're canceled out. And we're just going to total up what's left here. So we have H3PO4. Aqueous. We now have 3 waters here. Well, let's add them all together. 3H2O, double arrow. The only thing we have left here is PO4 -3, aqueous. And then we have 3 hydroniums here. So 3H3O plus. Aqueous. So just to put this in perspective, H3, it had 3 hydrogens. That means we needed 3 waters to get rid of all the hydrogens, and then we made 3 hydroniums. So if your acid had 5 hydrogens, it would take 5 waters to make 5 hydroniums. If it had 25 hydrogens, it would take 25 waters to make 25 of these. And that is about it. So this acid was triprotic. It means it had 3 hydrogens, ergo 3 steps.